Well, this is a practice talk for a DOE catalysis meeting talk to be given tomorrow, and I figured since I was doing this, I would just go ahead and make a web video. The focus of this talk is about how we can systematically model catalysts on amorphous supports, specifically isolated metal centers on metal catalyst supports. These are common catalysts in industry, and yet we really don't have a framework for modeling them. There are a couple of things that people do, but they are largely based on sort of ad hoc choices and how to build the models of the active site. And so that's the basic goal of this work, is to come up with some systematic way of modeling these special catalysts that are that really have given modeling such a challenge over the years. Now, hopefully my slideshow is working. Stop. Okay, I'm not really sure if my slideshow is working, but we'll make do with this. So there are many examples, and in fact extremely successful examples, where people have used ab initio calculations to model catalysis on crystalline materials. For example, there's a lot of work modeling catalysis on electrode surfaces, a lot of work modeling catalysis in zeolites, and a lot of work modeling catalysis in metal oxides, and in this case I believe this is a metal sulfide. So the key common denominator in all of these studies is that they're all starting from one paradigm. They go from some a priori knowledge of the crystal structure of the material on which catalysis occurs. They use that knowledge about the structure to build a molecular model, and then from that model they can predict catalytic properties of that surface. Okay? So the problem for modeling amorphous supports, again struggling with the buttons here, is that we don't really know what lives underneath these supports, right? So this is an example. This is a tantalum catalyst that has been grafted to an SBA15. This is a amorphous silica material, and when we draw these molecular models, we really just sort of put a line here and write SBA15 under them because we don't really know exactly where the atoms are. The walls are amorphous. Every one of these sites in principle is different. Now I note here that the author of this study, Tilly and coworkers, they have compared these sites to enzymes, and they are like enzymes in some way. They each have a well-defined coordination sphere around the active metal center, and it goes through a number of different states, turns over just like a catalyst, but every site here is a little bit different, and in that way they're very different from enzymes. And what we want to be able to do is to systematically and quantitatively explore the differences in that reactivity that emerge from differences in the local region to which this metal atom is grafted on this surface. Okay, so you could similarly look at cases like this, where we have just, for example, looking at other chemical properties like Lewis acidity or Bronsted acidity on surfaces, solid acid surface sites, basically. In cases like this, there are various ideas about how these things work. People draw these molecular stick diagrams to represent their ideas, but every one of these things, they always sort of terminate in free space here, and that represents connectivity to the rest of the underlying amorphous lattice. Of course, in reality, the different locations of termination, and particularly different ways of straining and stressing the bonds that are involved in this chemistry, are going to affect the energetics and the rates at which these processes happen on a given site. And so it would be really nice to be able to systematically go in and say something about how those differences modulate the reactivity of processes like this, or acidity in cases like this. So there are a number of protocols already for modeling amorphous materials. I would argue that really by necessity, none of them are very rigorous. So a couple of examples. Here is work looking at silsesquioxane, a model for amorphous silica alumina in this case. So aluminum has been inserted for a silicon atom here. And aluminum, of course, doesn't want to be 3 coordinated. And so the authors have put a siloxane group here to provide a 4th coordination site for the aluminum center. And then this 4-coordinated aluminum interacts with this pyrenate species, and when it does that, you see that what happens is the pyrenate basically strong Lewis base, it pushes aside the siloxane group that was placed here. Now that's fine. I mean, this is sort of the way the calculation was set up. The problem with this kind of approach is that it's probably unrealistically flexible, right? So this siloxane group, these silicons have moved by something like 3 angstroms. And if you really took silicons that were really part of a solid, which is what this model is supposed to represent, and you took a given atom and you pulled it out of place by 3 angstroms, you've ripped it out of the structure and torn all of the bonds to which it was attached to everything else, and really done some nasty chemistry, in fact, there. And so, here it's just free to float over. So these kinds of models where we just say we don't know where to put these silicon atoms, so we're just not going to put them anywhere. We're going to let them float around freely. Well, those tend to be too flexible, right? The alternative is that you choose some ad hoc position to fix those atoms in. And one of the typical ways of doing this is to carve a small cluster model out of a zeolite or out of quartz or cristobalite or something of that sort. And this is a common way of modeling localized amorphous regions on silica or silica alumina materials. The problem, of course, is that you don't have a whole large distribution of sites to choose from, and the sites that you're modeling are actually representative of the quartz or the zeolite that you started from. They're not really necessarily representative of those most active sites that might actually even be dominant in the reaction chemistry. So this is sort of a background of 2 of the main ways that people model amorphous catalysts in the past, and that by and large is basically what people do, various variations on these 2 themes. What we're going to do is to develop a systematic way of doing this. And when I started this work, some wise guys from, I mean that in the most positive way, wise, experienced experts from working many years in this field said, these are amorphous materials, you don't know anything about their structure, you're not going to be able to model these things, this project is doomed to fail. And of course, when you hear that, and you also simultaneously know that there are real catalysts like this that people want to understand how they work and don't know how to model them, to me that just sounded like it's a perfect problem. And so there, as I mentioned, there are many reasons to try and solve this. We have a lot of examples of catalysts that only work on amorphous supports. Examples like the Phillips catalyst, for example, for ethylene polymerization, and also from Susanna Scott's work, the MTO, methylrhenium trioxide catalyst for olefin metathesis, are just 2 examples that I've been exposed to since I started working here at UCSB. And what we would really like to have are something along the lines of structure-property relations. We would like to be able to systematically say, how do dead and active sites differ, and how are the strong and weak Lewis acid sites different? Now, when you model these things using ad hoc procedures, one of the first questions that always comes up is, somebody in the audience will say, well, what if you were to just take that atom, some part of your calculation doesn't agree with the experiment, and the suggested solution is just take that atom and move it a little bit. And wouldn't that change the activation energy or change the reaction energy a little bit and perhaps make things more consistent with experiment? And this is sort of a, I mean, yes, you can go in and start just moving things around, but if you don't have a rationale for doing so and you're just trying to create a model that matches the experiment, it's not really a very scientific approach. And so what we want is not to ask this question, how can you tinker with your model to get it to agree? We would rather be able to systematically answer a question like this. How do typical active and dead sites differ? That is, if I could generate a representative dead site and a representative active site, what would be the differences in their crystal structures? Okay, so in order to do this, we really had to sort of limit the number of possibilities to consider. And we started thinking about what are the characteristics of amorphous systems, amorphous solids in particular, and this is what we came up with, right? So imagine that you have a amorphous support with a molybdenum complex anchored to this support. It looks something like this, right? So here's our actual molecular model of that, and here's our stick drawing, right? So of course, when we go from the stick drawing to the molecular model, we have to choose a place to put these anchoring positions. And in a sense, this talk is all about that. So these anchoring positions are shown here. And I sort of draw this line through this diagram that separates the parts of the structure that we know, for example, the conductivity we might know from x-AFs. Down here we have no idea what's going on. It's gotten too far away from the center of our reaction to be able to say for sure where these atoms should go. So we're going to call these atoms down here the periphery atoms, and the atoms inside this region where the reaction is going to be occurring, we're going to call them the interior atoms. Now we can establish a couple of guidelines for modeling these things. One, because we don't want our sites to be too flexible, we want these periphery atoms to be immobile. That is, we want to, once we establish a position for them, we want to model the whole reaction chemistry with those atoms fixed in place, as we expect that they are. Once you've calcined and made your catalyst, you don't expect that while you're running it, it's fluidizing and totally reorganizing on the surface. Those sites are what they are once they're made. Okay, so the second guideline is that these periphery atom positions, we know that they influence the active site properties. You know, if I take this thing and I stretch these two silicon anchor points apart, I will end up with an active site that has slightly different properties. And the third guideline here is that we know that there's really, in an amorphous material, there's a continuous distribution of different places where I might find these silicon atoms, right? So it's not like a zeolite where there's a discrete number of possibilities, some certain number of unique T atom centers, for example, where if I modeled all of those, then I've included everything. Here we actually have an uncountable number of different arrangements to place these periphery atoms. Okay, the fourth point to make here is that for any given activation energy on this site, suppose I were to compute the rate on this site and compare all sites that have the same rate. Okay, so I can look at, you know, there are of course sites with different rates, but I'm going to look at just the ones that have the same rate. There are probably many ways to get the same rate on a given site, same turnover frequency. And what we expect is that the site that has the lowest energy among all of those sites that have the same turnover frequency is the most common site with that turnover frequency, right? This is really basically the same. It's not quite assuming a Boltzmann distribution, but it's assuming that we have some distribution for which the population favors low energy sites over high energy sites. And of course, we're still going to have a distribution of sites at all different activation energies, right? So these are the sort of four premises. And I want to point out that this one is actually really important. First of all, it's the one that's an approximation. And second of all, it's the one that's going to allow us to make some progress on this problem. So we are making an approximation here. We're well aware of that. But we think it's actually a reasonable one, and certainly something that people rely on when they do DFT in other contexts, always assuming 0 Kelvin properties are relevant. Okay, so we're going to go ahead and go forward with this, and we are going to see where it takes us. Okay, so a little review of how cluster models work in other contexts. Okay, so imagine that you're doing a calculation with a cluster model of a zeolite. You have some energy function. It's a function of both the atoms close to the reaction center, my interior atoms, the atoms at the periphery of my cluster model. Those are the guys out at the very edges of my model. We usually, in a zeolite case, we fix those into crystallographic positions. And we also have, of course, an energy that's a function of the electron density. Okay, so electronic structure codes already do this part for us. They give us the Bohr-Oppenheimer energy as a function of only the positions of the nuclei. Now we have a function that depends on the positions of our interior and periphery atoms. Now, what we do is very standard. We have two different kinds of optimizations that we do. We fix these periphery atoms in place, and we do a minimization to get the reactant energy, right? So this is now my energy of the reactant state, and it no longer depends on the interior atoms because those have been optimized. It does depend on where I put those periphery atoms still. Okay, so we're going to keep that argument in this variable. We also do a transition state optimization, and so again the dependence on the interior atoms vanishes because they have to be at a transition state in that interior space, and of course that transition state energy we also expect that will depend on these periphery atom positions. Okay, next. We recognize that that if we were modeling a reaction in a zeolite, we would be finished, right? So all we would need to know now is that the activation energy is the difference between the between the transition state energy at this periphery position and the reactant energy at this periphery position. And, apart from some corrections involved in estimating the rate accurately, we're done. Okay? So the problem that we face for an amorphous material is that we know that these XPs matter, and we don't know where to put them, right? So this is the last part, right? So we have an amorphous material. We have no idea where these periphery atoms are located. All we know is that there's a continuous distribution of them. So what are we going to do? Well, we're going to solve a third level of constrained optimization, right? Here was one. Here, at the second level, there's a minimization and a saddle point optimization. And now I'm introducing a third level of constrained optimization. In this level, we're saying that we have we want to find the lowest energy site that gives us this target activation energy, right? So this is a constrained optimization, and the constraint is not your typical constraint that involves a bond length or an angle or something like that. This is a really difficult constraint. This is a difference between two energies with fixed peripheral atoms. And then we're asking, okay, inside this calculation, you're doing all these constrained optimizations of the interior, and we now want to ask, for all the possible peripheral atoms that you could have picked, what is the one that gives you the lowest formation energy of that reactant site? Okay, so this is basically the framework that we've set up here. Now, this turns out to be an extremely expensive problem if you just plunge in and start trying to do these constrained optimizations. And after about a year or so of trying to get this to work, I had spent the patience of 1.5 graduate students. I say a half because one of them changed projects, didn't quit on me. And I was really starting to wonder, were the sage old experts who told me this was an impossible problem, were they correct? And then I went back to my books. My wife makes me read them. I buy them, and then she says, "You can't buy another one until you can tell me that you've read that one." So it's good for me. But anyway, so I went back to my books, and I noticed that there's this sequential quadratic programming framework that seemed perfectly well suited to solve this problem. Okay, so here's how it works, right? So we have an energy of the reactant state. We can expand that for any displacement in the interior atoms and the periphery atoms around our current position in just a second-order Taylor approximation, okay? We have now, we're going to do the same thing with our transition state, right? So I've got two second-order Taylor approximations. One describes my reactant state and one describes my transition state. And then I'm going to think about what happens when I change the interior, right? Or what happens when I change the periphery? Well, I can predict from a change in the periphery where the new minimum location for the interior would be, and also where the new transition state location in the interior would be, right? So you can think of this basically like this. We're sitting at this point, and we now have optimized. This point is at a optimum, energy minimum, among all possible peripheral coordinates at this value of the peripheral coordinate. Now we're going to kick this peripheral coordinate to some new location, and what will happen is that we will have to re-optimize this interior coordinate to adjust for that change that we made in the periphery. And this can all be done in quadratic approximation analytically. Okay, now in the third step, what we're going to do is we're going to write down the reduced energy landscape using this interior as a function of the periphery change. We can eliminate entirely the interior optimizations from this problem, right? So now the advantage of doing it this way is that the interior now is going to adiabatically follow the periphery. As long as I make small perturbations to the periphery, I have unnested this problem. So basically I can now think about a reduced energy landscape which only depends on where I put those periphery atoms. Okay? So now let me just show you how this would work in terms of an empirical valence bond model, right? So if I start with this thing, there's one step that I haven't really described, and that is how do you find a point on this curve, right? So you can imagine finding a place on the curve that corresponds to that third level constrained optimization problem. Right? So I have to find one configuration that lives on the locus of points that satisfy that problem. Here's how you do it. You say, I'm going to just forget about the constraint, okay? And I'm going to minimize the energy of my reactant site. Okay? So this gives you a point that lives right here, okay? And of course, that is a site, and it has some activation energy. And so it's actually a point on your curve, right? It's a point on your curve that happens to have this activation energy as though you had done the constrained optimization. All right, now that we've got 1 point on our curve of reactant states and 1 point on our curve of transition states, we don't really know, so we're cheating here because we can see where these two curves lie in space. This is the peripheral coordinate. It's a very simple two-dimensional model, so I've got one peripheral coordinate, one interior coordinate. That must be my reaction coordinate. It's all that's left. And so what we're going to do now is to go through and start applying the sequential quadratic programming algorithm. So the first thing that we do is we dial up we check for sites that have slightly larger activation energies, that is a delta delta E dagger, than the one that we started with, right? So we started with this activation energy, and we're going to ask, how would I modify this site? That is, how would I move the peripheral coordinates so that the activation energy of that site goes up, okay? And here you see it's a step to the left, right? When I move to the left, the gap between the reactant state and the transition state is getting higher, right? Okay, so we keep doing this, and we keep doing this, and we walk all the way, we walk all the way till we get to the end. And then the next thing we do is we turn around and we go from our minimum back the other direction. We say now, so what we just did was we generated a whole bunch of dead sites, right? So these are sites that have higher activation barriers than the one that we started with. So we're going towards dead sites this way. And now what we're going to do is turn around and walk the other direction. We're going to go to lower and lower activation energies. What we're doing here is generating more and more active sites. Okay? And we're doing this systematically, right? So the path that we're following is guided only by the criteria that I want the activation energy to get bigger and I want the activation energy to get smaller. In fact, it is sort of answering the question that I posed to you in the beginning, the sort of ill-posed question where people say, let me just try and move the atoms around so that I get a higher activation energy. Well, this is telling you exactly how you should move the atoms so that you get a higher activation energy without paying a lot of site formation energy price for doing so, right? So if you were to find sites with low activation energies, for example, and you didn't want them to be impossible to find or impossible to make, they should have low site formation energies, and this is sort of probably the nature of those kinds of sites, is the thinking in this algorithm. Okay, so now what we're going to do, so we have this little two-dimensional example that I've just shown you, but of course in real problems we have some 30 or 100 dimensions depending on the number of atoms that we have, and these paths will be impossible to see. But what we can still see is we can look at the activation energy as a function of the site formation energy, right? And this traces out a curve in space. We start from very, very active sites, which have high site formation energies, right? So these are going to be rare sites, we expect. Then we start moving down towards common sites, but those have higher activation barriers and probably are less active. And eventually we move all the way out to completely dead sites. Those are actually hard to find as well. And there's no reason to want to find them, I guess, if you're making a catalyst. Okay, so let me now move towards an atomistic example, doing this with actual ab initio calculations. Okay, so this is a really nice work done by Jaroslaw Hanslick back in 2007. And Jaroslaw thinks about these things very carefully. He recognizes that you can't just study the chemistry of an amorphous catalyst by constructing one site. You have to look at variations on that site and look at how those variations influence the reactivity. And so he's looking at catalysis of olefin metathesis by isolated molybdenum centers on amorphous silica. Okay, and as a model for amorphous silica, he cuts these little clusters out of beta cristobalite, and he actually embeds them. I shouldn't say cuts them out, because they are actually embedded in a sort of QM framework. So this is B3 lip embedded in a Hartree-Fock kind of framework. Okay, so here is the transition state of the reaction that he's modeling here, and here is the most abundant intermediate before that transition state, right? So this is the relevant gap in energies that we're interested in, is the one between this species and this species. Okay, so now here's what Jaroslaw Hanslick does. he says, well, we can't just model one site. We have to now consider all the variations on this site and the way that those differences in those sites affect the reactivity. So he constructs 10 different models, cut from different parts of the beta cristobalite surface, protonated differently, terminated differently, etc. Okay, so these are all subtly different variations on the same theme, and he's modeling the same chemistry on every one. And I have some animation problems, clearly. And I will show you in a moment what he finds, but I'm going to now show our approach for doing this. We're going to start with this very, very simple little cluster model. We take a model that's just, all we know from XAFs is that molybdenum is connected to, through oxygens to 2 silicon centers. This is how it's anchored to the surface. We know some things also, I guess, about its coordination sphere as well. But basically, according to Hanslick's work, it goes from a trigonal bipyramidal complex through this metallocycle rotation transition state and makes this square pyramidal complex. And this is all sort of a trap that stops the Chauvin mechanism from working. Okay, a couple notes about the model chemistry here. We use some basis set deficient fluorine atoms to try and mimic the electron withdrawing capability of these OH groups. And for the interior, for everything else, we used, there must be some model chemistry there, I hope. Okay, I didn't say, okay, I see what this means. So the interior is everything except for these fluorines, right? So all the atoms are free to move except for these 6 fluorine atoms in our cluster. Okay, here are the results. You see that the activation energy spans from 30 kilojoules per mole, really, really active. This is going to turn over really quickly, all the way to 70 kilojoules per mole, right? So this site is basically dead now, right? So in comparison to that one, at least. And that's a really remarkable range, right? So the answer to this question, you know, what if you tweak your model of the active site a little bit? Well, you can change a lot, right? Now notice the 10 sites that Hanslick made, which were all carved from crystal structures, they all have similar low energies of formation, and they're all very near the same range of activation energies, right? So it appears that doing this in this rather ad hoc way, choosing a crystal and cutting things out of it, really doesn't capture the wings of this distribution well. In fact, you could argue that it's missing a big chunk of the distribution. And when you rate weight the distribution, that is, when you ask the question, if I have sites that have populations according to something like a Boltzmann factor, but then I multiply that Boltzmann factor by the rate at which the catalysis happens on that site, that shifts the whole distribution to the left. And you can make an argument that the dominant part of the distribution of sites, at least for catalysis, is over here on the left, probably entirely missing this part of the distribution of active sites that was studied by Hanslick. And so I think this is a nice example because it actually suggests, you know, notice that Hanslick's models were 35 silicons and he had 10 different models in order to get these kinds of results. We started with one model. We just systematically and continuously transformed it from one model into the next, and each time we get a slightly different activation energy as prescribed by the sequential quadratic programming algorithm that we've developed. And we managed to span a larger range of the reactivity, and to the extent that our thinking about this is correct, we're getting things out of the range of what had been seen before and significantly different in terms of their activation energies and their activities from what the standard approach would find. Okay, so now you know, what can we extract from this? Remember, one of our key goals was to find structure-property relationships on these materials. And so we can do that. It's a pretty simple little site and pretty simple chemistry in this case. But you can definitely see that it predicts that as you go to very, very high activation energy sites, those are the dead ones, the distance between the 2 silicon anchors to the amorphous support, they're getting farther and farther apart, right? So it appears that stretched sites are less active than sites where the anchors have been pushed together. And so that's an interesting result. It's sort of something that might tell you something about where your dominant source of reactivity is coming from. Of course, the kind of descriptors that we would really like to get at are the kinds of things that might inform us how to synthesize a more active site. For example, do sites that are more active bind to some target robust Lewis base very well that you might be able to actually include in the synthesis and actually mold active sites around some sacrificial molecule to then burn off later. Those are the kinds of things that I think would be really, really nice if we could do. And of course, that's a bit of a dream at this point, but it's something that we're working towards and thinking about. All right, so how do we relate these things that we're doing to measurements, right? So the whole idea here is that we have sites, a whole bunch of different kinds of sites, and I'm going to represent their geometry in this abstract variable x, right? So this just represents the local geometry of the region to which the metal center is anchored on the amorphous support. And every local geometry corresponds to some characteristic activation energy, and I'm going to sort of switch to elementary statistical mechanics notation here. Beta corresponds to 1 over Boltzmann's constant times temperature. And so at every site, I've got a characteristic activation barrier and a characteristic prefactor. And if I had all the sites were exactly like this one, I would just get a nice simple Arrhenius plot, and it would account for everything, right? But of course, the rate that you measure is actually a mixture of the reactivity happening at every one of those different sites. In fact, if you could think about having some density of different sites, and this is the rate equation for every one of those sites, then the rate that you would measure would just be an average of the rate on every individual site. Now, this is a very inconvenient way to think about this problem because we, of course, can't look at the sites individually. But we might be able to get a little bit closer to relating things to experiment if we can make a projection onto the density of states. Now, I use the term density of states because it looks exactly like statistical mechanics here, what I'm doing. I have a density of states with an activation barrier now, not with an energy, but now with an activation barrier, delta E. And this now is the rate, the average rate for sites with this activation barrier, delta E, right? So this is now an average prefactor. And this is an equivalent way, in fact, no approximation in writing things this way, because of the definition down here. If you care for the statistical mechanics, knock yourselves out and go through and derive this. But the key point here is that the average rate can be written exactly in terms of a modified distribution of states, a density of states, phrased in terms of the activation energies themselves. Okay, and now, again, appealing to this elementary statistical mechanics analogy, we can take the derivative of the logarithm of the average rate with respect to 1 over kt, right? This is the slope of the Arrhenius plot, effectively. And you see what comes out is not really quite the activation energy itself or the average activation energy. It's this rate-weighted activation energy, okay? So what do I mean by rate weighting? What I mean is that for any variable y, I can compute the average of y with a rate weighting by multiplying by my density of states, multiplying by the rate at that activation energy, and then integrating with y, and then of course I have this normalization factor here in the bottom. Okay, so that's the definition of this J-weighted average. And one of the things to point out here is that this is not the same as the average activation energy unless all of these sites are actually the same, right? Which of course is probably never really the case. Now, we can go on and we can do what we would do in statistical mechanics to find the heat capacity. We can take a second derivative of the log of the average rate with respect to 1 over kt squared now. Okay, and this gives us a variance in the activation energy, right? So this now should correspond, just from the definition of where we got it, to curvature on the Arrhenius plot. And so the implication here is that if the sites on the material are very, very different, if there's a really wide distribution of different activation energies, that might show up as observable curvature on an Arrhenius plot. Okay, well, let's take a little model, right? So let's take a little model where we just assume that the density of states with different activation energies is Gaussian in the activation energy itself. So there's a little standard one-dimensional Gaussian. We can go through, we can do all the math that I showed you on the last slide, and we find that the slope of the Arrhenius plot is delta E0, that is the center of the Gaussian, minus beta times sigma squared. So you subtract a factor that has to do with the variance of the Gaussian. Okay? Now notice that it's not the typical site that determines the activation energy. Okay, so if you're finding the lowest energy site in your system, you're probably something like this guy, and you're missing the boat, right? The Arrhenius slope that you see the one thing that we can pull out of experiments from this thing is really related to, it is related to this typical site, but it's also related to the sort of width of the wings of the distribution of activation energies, and also to the temperature at which you do the measurement, right? So what about the curvature, right? So I mentioned that you would have curvature, and for Gaussian, it actually just ends up being the variance of the Gaussian distribution, right? That's the way this thing works out. Okay, so let's take some parameters, right? So I showed you this calculation by Brian Goldsmith following up on the work of Hanslick, and I showed you that we had this distribution of different activation energies. If we take their distribution, it's mine too, and we now come up with a Gaussian that has the same mean and the same variance, that would have a mean activation energy of 53.1. And this is not rate averaged. This is just the mean for all the sites, whether they're reactive or not. And we have a standard deviation in those activation energies that's 11.5. Okay, so pretty wide Gaussian here, quite a spread in activation energies. And we can look at what the Arrhenius plot should look like from this. And you do see curvature, right? So there's a little bit of an observable curvature here. The problem is that you probably will very rarely see, in the experimental literature, an experiment that measures rates over 250 Kelvin temperature interval, right? I mean, in order to see this curvature, you have to go out really, really far. If you were only looking right here, or if you were even looking over this wide interval and had some error bars, you could easily miss that this curvature was present. Okay, so I don't really think that this is the best way to understand the nature of the activation energy distribution on your amorphous catalysts. Are there other ways that we can do it? Well, my colleague Susanna Scott suggested this one. She said, you know, one of the things that we do is this technique called active site counting, and they can get an idea of what fraction of the catalyst sites are responsible for what fraction of the activity. For example, you can quantify the question, what fraction of my sites are doing 90% of the turnovers on this reaction? Okay, and you know, that's it. It's an interesting set of experiments, and I don't know how to explain exactly what those are doing or how they work. But let's go back to this example from Goldsmith, and let's try this idea, right? So we take a Gaussian approximation to the calculations of Goldsmith and coworkers, which includes myself, and this is the actual distribution of site energies. It spans, again, from about 30 kilojoules per mole out to about 75 kilojoules per mole, pretty wide range. And here's what happens when you J-weight those distributions, right? This is the thing that determines the average activity, and the curvature of that Arrhenius plot is this J-weighted distribution. And here's what it's doing, right? So these sites are extremely active, but there are not very many of them. Yet they're so much more active than the other sites. You see that the peak is now moved all the way over here to some sites that we didn't even really generate these, right? So you know, our error in our Gaussian approximation is becoming quite questionable here, whether we can really apply this. But to the extent that it's really a Gaussian approximation, we have at 376 K, we have what would appear to be an activation energy of around 15 kilojoules per mole or so. By the time you increase that to 610 K, you've got an activation energy that now is looking somewhere between 20 and 30 kilojoules per mole. Okay, so how about that active site counting experiment? Well, what happens when you move the temperature across here? We can trust these results when we're at high temperature at 601 K. You see that about 30% of the sites are doing 90% of the turnovers, right? As you decrease and decrease and decrease the temperature, you get down to a point where these Gaussian tails are clearly going to negative activation energies, and that's probably just an artifact of the fact that we assumed a Gaussian distribution here. I wouldn't put too much stock in this, but you can definitely see the trend that as you run this catalyst at colder and colder and colder temperatures, the site distribution doesn't change, right? Once you calcined that catalyst, you made a catalyst at 700 Kelvin in this example. That's where we got these numbers. You made this catalyst at 700 Kelvin, and its sites are what they are permanently. Now you lower the temperature, the wings of the distribution are still there, and at lower and lower temperatures, they become more and more heavily contributing to the average rate. Now that average rate is dropping, mind you. The turnovers are all getting slower, because the temperature is dropping. But the sites that are doing the turnovers are increasingly these sites farther and farther and farther out on the distribution, which are fewer and fewer fraction of the total sites. And I think when you follow the arguments that led to this quantitative analysis, you realize that, probably we should expect that when you synthesize a catalyst by some calcination process at very, very high temperatures, and then you rapidly quench that catalyst, you have frozen in a bunch of local geometries that are representative of a very high temperature. And then once you operate that catalyst at a lower temperature, those sites aren't going to change. And so you should expect that that broad distribution of different local site geometries is going to give rise to a phenomena like this, probably in many cases, right? So I think that what we should expect is that, if the site was made at high temperature, it has a long tail of different structures. A long tail of different structures probably means also a long tail of different reactivities. And a long tail of different reactivities means that you should see this declining fraction of sites contributing to your reaction rate as a function of the temperature on operation. And so, I think that there are some kinds of predictions that we're beginning to be able to make. This is work that is definitely new. There was nothing like it in the literature before. I won't say that I think that it was right, but I think it's a step in the direction of being able to think about these things in a quantitative and systematic way. And I look forward to seeing lots of other innovations in this direction in the future, because obviously these are important catalysts and we need to understand how they work. So I want to just point you to the paper in the literature. This is a JChem Phys publication. Brian Goldsmith is the lead author on this. He's really a dynamo of a graduate student who did a tireless job following through many hurdles and bugs and things along the way in order to get this working. Some talented undergrads worked with us as well. Daniel Bean helps us with our computer deficiencies, and Evan Sanderson helped us build the capping atoms that we used in these calculations. The take-home message here is that if you want to model in any systematic way catalysis on amorphous supports, you can't go from some a priori knowledge of the structure to the property. You're going to have to figure out some inverse algorithm to go from properties to structure. And that's what we've done, at least in a first approximation. And our algorithm generates low energy sites with different activation energies. And then we use that spectrum of different sites as representative members of the whole ensemble of different sites, so that we can contrast the structures of dead and active sites and hopefully learn some things about what leads to different levels of reactivity in that distribution. And then the final bit of the talk was about linking the distribution of activation energies to observable features. For example, Arrhenius plots and active site counting results. I want to thank Susanna Scott. It was problems suggested by her when I first arrived here to UCSB that really motivated this entire line of work. I joke that when I got here, she kept asking me to do impossible things, and then I eventually realized that they were really, really rich problems, and so I'm grateful to her for that. A number of other colleagues and students have helped me along the way, and I thank them as well. And of course, we've been patiently funded through this very original endeavor by the DOE, the NSF, and also the Petroleum Research Foundation. And so thank you to you all.